So with all of the discussions we've had over this last week and a half or 2 weeks, most of it is centered around this concept of proportionality. So I ask a very general question here. What does proportional look like? And what I mean by that, let's do kind of like a word association thing, where when I say the word proportional to you, what comes to mind? Like, what do you think of when you hear me say proportional? It can be a word, it can be a phrase, it can be an example, just anything. Let's just start putting them out there. What do you think, Amelia? Yeah, a linear graph that passes through the origin. That's proportional. What else? Leah? Steady rate. Okay? Anything else? Ellie? Constant increase. That constant, that steadiness. All right. Anything else? What my other group talked about, they said K value, the constant of proportionality. The K value also means what? What does that symbolize? When I say find K, find that constant of proportionality, you're finding what? The unit rate, exactly. Or the slope. Some of you maybe call it the slope, but that's not as prevalent for us anymore, or at least at this point. So that's what we think of when we think of proportionality. Well, the formal definition here, just for what a proportion is, it's an equation, but it's talking about two ratios that are equal. That's what a proportion is. And in our bell ringer, we actually did a proportion. The way that some of you chose to solve it, you did it in terms of solving a proportion. But let me just give you some basic examples of what proportions look like. I could say something like 3/4 is equal to 12/16. Those are equivalent ratios. So we would say that that forms a proportion. 5/4, 100/80. 1/9, 2/18. I don't know. You can do this all day, right? Just two ratios that are equal to one another. That's what it means to be proportional. But what we're going to be looking at are proportions that have unknown values in them. You guys have spent a lot of time with equivalent fractions and things. That's no big deal. But when you start looking at proportions that have unknown values, then that means you have to solve them. Like we saw up above, we referenced the word equation when we were writing this definition. Well, we spent all that time solving equations, and that's kind of what we're going to be doing here. So let's just say I give you an example. 12/15 or 12 to 15 is equal to x to 10. And I know you guys can do this. I want you to find me the value of x. It's going to make this a true statement. But the answer to me is not even close to being as important as the method in which you're finding it. So I want you to be able to articulate how you found this number when you finally get it. So go ahead and try that. Oh, just give me a little time. Okay, so x. What is it? What'd you get, Brady? Anybody else get x is equal to 8? Okay, good. So how did you get x equals 8? Mm-hmm. So you said when you divide 15 by 2/3, you get 10? Is that what you're saying? 15 divided by 2/3 is the same as saying 15 times 3 over 2, and that wouldn't be 10. Well, I mean, you got the right answer, so obviously whatever you did was correct. I think what you wanted to say was 15 times 2/3. You're finding 2/3 of 15, and that's 10. So now you're trying to find 2/3 of 12. So you could take 12 times 2/3, and that would give you 8. So yeah, that's right. Did any of you do it like that? Did any of you think of the 2/3 relationship? No? Give me a different way then. Go ahead, Sarah. 15 divided by 10. Mm-hmm. Okay. 12 times, I was going to say 12 times 1.5 would be 18. But yeah, 12 divided by 1.5 would equal 8. So think of it like this way. She divided this way. She divided 15 by 10 to get 1.5. So divide by, excellent. Up here, you divide by 1.5. When you're going in the same direction, you do the same operation. Do you have a different way, Mikey? Mm-hmm. Very good. Anybody else reduce 12/15s down? And when you do that, look at the factors here. 5 goes into 10 twice, so you just double the 4. That's kind of like our bell ringer question. For those of you that said you did it the way Zoe described, when she said she took 3 times 4, that's what we're doing here. It's scaling it up. It's like a scale factor method for solving them. Okay? Any other ways? Go ahead, Zoe. And that gives you 8. So dividing, she divided down. So when she went down this way, she divided to get 0.8. So then when she's going back this direction, she's going to do the inverse operation. So she wouldn't divide this by 0.8. She would multiply it by 0.8. Okay, Ellie? Go. Yeah. Yeah. Well, and that's kind of goes back to what Brady had said earlier, because 10 divided by 15 is equivalent to 2/3. So then you're doing 2/3 times that. So you looked at it as a decimal, he looked at it as a fraction, but it works out the same. Did anybody divide 120 by 15? No? Okay. Let me show you something. Go back up here, and let's just look at, let me just give you one at a time here, so we focus in on this guy. That one. What do you notice about the products of the term in the numerator on the left side and the denominator on the right side versus the numerator on the right side and the denominator on the left side? What do you notice? Quinn? Okay, so what I'm saying is, what do we notice about, oh, he's not going to let me draw. What do I notice about this product here and this product here. What do you see? Yeah? I agree. I'm thinking even more simple than that. What's 3 times 16? What's 4 times 12? All right. Well, does that logic apply here? 4 times 100, 5 times 80. Do you get the same product? Okay. Now remember, we said all of these were proportions. How about here? Yeah? Okay. So would you guys agree that this is, are these equivalent, these proportional? No, 2/3 isn't equal to 3/4. Test that same method. Do you get the same product? No, you don't. I'm going back even farther here. I'm going back to something we did a little while ago. Remember we did these when we first learned about proportionality? Remember what distance a car drives down the street? We've already solved all of this. If you look at just this first set right here, the ratio of 1 to 24 and 2 to 48, do you get the same product? Yeah, I can test this throughout. 2 to 72, if I multiply 2 by 72, I get 144. 48 times 3, 144. It's going to work every single time. All right. Well, you remember the number of baseballs versus the total cost? We said, no, this is not a proportional relationship. And now you can see why. Because if I test it, it's not going to work. Now, what? You might be thinking, why are we worried about this? Well, another possible way to solving this proportion, and I know I've got it all junked up here with the writing, but would be to take 12 times 10 and you get 120. I'll let it think about that for a little while. Oh, it just shut me down. All right, we'll talk through it. 12 times 10 is 120. And then I have 15 times x. So 15 times x should equal 120. 120 divided by 15 would give you that product. All right, if you turn that over, I'll see if I can locate my notes. But well, I guess, no, I'm sorry, you don't have to turn it over. It's actually right beneath there, where it talks about the 2 methods for solving. The one method, the first one we're going to write down, we're going to call that scale factor. So on line number 1, let's all write scale factor for that. On line number 2, write cross products. I found it. All right, good. So scale factor. Now, those of you that said, like on the bell ringer, that you just took 3 times 4 and then 750 times 4, you use this concept of scale factor. You figured out how many times the one number goes into the other. In fact, going backwards, for those of you that did like Brady's way, the first way, that's considered scale factor, because he figured out how many times one number went into the other, and then he multiplied or divided the other numbers by that. The other method was the cross product method, and none of us used it, but I bet many will pick up on that and use it more consistently here. So let's try something. See how it says method 1, method 2. I'm going to give you 2 different examples. Method 1 is to use the scale factor way, which is the way, again, that pretty much everyone used the first time through. So if I give you something like 5 to 8, keep it basic here, m to 40. So 5 to 8, m to 40. Find a value of m, and I want to know which way you did it. Underneath it says example 3. I'm actually going to write the exact same thing. Maybe. I'm going to take this exact same thing and put it down here because we're going to do it a little different. What's m? What does m equal, I should say? What does m equal? Isaac, 25. I think we all would agree that m is 25. Now the scale factor way says, I look here and I look for how one number could go into another number. And how many of you notice this connection between 8 and 40? Right? Scale factor. It's saying, well, if I multiply 8 by 5, I'll achieve that 40. But to be consistent, you guys know with equivalency in fractions that you can't just multiply the denominator by one thing without doing the same thing to the numerator in order to maintain that consistency. So you have to multiply that by 5 as well. Okay? And that's how we could come up with m equals 25. Method 2 says, all right, well, I know that the product of 5 and 40 should be the same as the product of 8 and whatever m is. Well, 5 times 40 is what? You can just say it. 200, yeah? What do I do with 200 then? Leah? Yeah, so 8m should equal 200. So what do you do with 200 here, Leah? Yeah, it's a one-step equation. You divide it by 8. And you're going to see that you get m is equal to 25 going that route too. Okay? So when you're doing the cross product way, I don't need to see this. I don't need you to write out the equation unless you want to, but that's not something I'm checking. But that's what cross product means when you do it that way. All right, let me give you a second example here. Let's go m over 3 and 21 to 26, let's say. Try to do it both ways. Same problem. Two methods here. And no, this one does not come out nice and neat and pretty. This one's kind of ugly. So if you have to round, which you will, round to the tens place on this, please. just don't close that because it'll lock. Somebody help me out with a proportion here for example 2. The one you used. Good, Sarah. Okay. Now, how many of you did the exact same one? I mean, aside from maybe the variable being different. That was pretty common? Okay. Good. What'd you end up getting, Sarah? Yeah, why'd you round? Because that should have been, it came out to be like 16. But I like her answer. Why'd you say 16, Sarah? Yeah, you're talking about how many how many can they make? Well, we wouldn't consider 2/3 of a package a full package. So in this case, you had to round down and say 16 care packages. But this was the right proportion, so I like that. All right, next one. Eagle team, teachers are ordering pizzas for the entire team. That's a lie, but if we were, 9 pizzas feed 25 students. How many pizzas will they need in order to feed all 120 Eagle team students? Give me the proportion. Go ahead, Allie. What do you have? Okay, so P, 120 students. I assume most of you had that same type operation set up. Okay. What did you get for P, Ellie? 43.2 pizzas. So another question here. What do we do with that number? Because I doubt any pizza place is going to sell you 2/10 of a pizza. Jack, what do you say? This one's one where you would round up. Right, yeah, in this case you want to make sure you round up so everybody gets the exact same amount, or at least they all get minimally the same amount, okay? So tonight, guys, you have tier 1, tier 2. My advice would be most of you should probably do tier 2. Tier 1 would be more the basic stuff, like, you know, the solving of the proportions I'm a little iffy on. Tier 2 is more of the advanced level on that. So if you feel very comfortable with what we've been doing, which it seems like you are, and I fully expected that, then I would recommend tier 2. But pay attention, because some of them are going to say write a proportion for this. So I want to see that proportion in your work. Okay? All right, we're going to stop right there. Good.